create a soup. Okay, we have some ingredients, tomato, salt, and then this is our first dish. Okay, see how it looks like. Overall, the first work is about a general technique which can somehow translate or translate a bunch of inputs into output, which is something we want. Okay, so you take input some credential schemas based on Sigma protocols, and then the output is something we really want. Which means what we really want is the service provider has a policy, and then the users, they have certain credentials. They can convince the service provider that they are legitimate or authorized without leaking whatever they have. Okay, that's something we want. And then we have a kind of BG by our side product called identification, which is an interactive version of the assembly signatures. So basically, in typical access control, you come to some server, you do some interaction, one round or multiple rounds, and then you get approved, and then you can get access to the resource you want, right? So this is actually in that scenario of access control. So there is another thing quite interesting is that this construct or this dish has a property which we would call inherent collaboration enabler. So you can see it as a feature, and you can also see it as a tag. So in this sense, say this building has the gate has a policy, which means under certain circumstances you can get into this building, right? So if I have all the credentials, then I can get it. But what if I don't? I only have some of them. So if I have a friend who has others, which if we can put them together, then we can get into the building. So using this is a tag or a feature. Sometimes in certain applications it would be a feature, but under certain other circumstances using it as a tag because you don't want people to collude, right? So if it is a tag, then we need to take care of it, right? So even saying this is another manifestation of what I would like to dark side of distributed crypto system. So like a threshold crypto system, people know very, very useful, but as we showed in our paper 2 or 3 years ago, in certain cases, you can actually abuse the threshold crypto system to do the very bad things. Okay. So this is the full spectrum of what we would expect for. On the one end, if only one side want to protect something, if nobody want to protect something, then you can achieve the best performance. So just show, okay, I want this kind of credential, and then, okay, I have one of them, I just give you, right? So it's best performance you can expect. And on the other hand is that if both are very cautious, they don't want to leak anything, unnecessary. So you can expect that the protocol would be very expensive, many rounds and many marginal explanations and so on. Okay, so here we stand. This work we stand in the between. So because we here do not protect the policy itself, but we want to protect the privacy and anonymity of the service requester. So we can achieve some like practical scheme. Okay. And then for the assembly signature, of course, you need to define what that means. Okay. This is really something like kind of pushed by the crypto community in the last decades or so. So you really need to define. So here we need to define like you need some bootstrapping system, and then you need to maintain the system when people join or leave, revoked or did something bad expelled from the system. And then of course you need a signing algorithm and verification, which basically means how the service requesters interact with the service provider, right? That's the most useful things. So for such a construct, we need to precisely define what does that mean when we say it's secure. Okay. Yeah, of course, we need it to be correct in the sense that if you do possess the credentials which satisfy the policy, Okay, you should always be able to get in the house, otherwise it's useless, right? And then on the other hand, even if you include, or not you, some bad guy who has access to credentials, and collude with many other people, they have legitimate access to credentials. Even they collude, they cannot fake any single parts. Otherwise, there is unauthorized user who can get in the building, then bad thing could happen, very likely, right? So that's intuition. And the anonymity means that, as I already mentioned, the intuition is that the service provider or the verifier cannot infer who exactly you are among the large candidate pool. So there are, for example, so we can assume the service provider or the adversary knows that there are, say, 100 people who possess those credentials, right? Because you have the credential issuing process or authority, right? So they know which people have credentials. So even this kind of information is linked to the adversary can still not get anything more than, say, 1 over 100. Okay, so basically a random guess. So in that count, so we can even actually just consider 2. So we just let the adversary to guess. So the adversary can make a guess with a probability significantly more than 50%, right? So this is kind of a standard definition in cryptography. So if that is achieved, which means if the adversary is forced to do random guess, then we say we achieved something we like. So that's a desired property. So this is the formal definition. And then it's kind of interesting that in order to prove the properties of this assembly signature schemes, somehow I cannot directly prove it. So we kind of introduce something else, and then we were anyhow finally we'll get there what we want. But just like it's not something you cannot go. I cannot go directly. So we define the identification scheme, which is kind of the interactive version of the assembly signatures, which is non-interactive. So you see the policy provide a signature, you get it into the door. Okay, here maybe we have some interaction. Okay. And then we define 2 properties for the interaction scheme. One is what we call strong security. It, of course, still require correctness. And then we define what is called extended spatial summaries. So it's extended from the spatial summaries for the underlying Sigma protocols. Okay, so it's kind of a generalization, and this says basically the same thing, but just like in a bigger context. So if you can answer the same challenge twice, then I can get a bunch of credentials which correspond to a satisfying assignment. So that is fundamentally the same as a single standard Sigma protocol. But here we're kind of a composite or compound. Okay. And the other property is also a generalization of the honest verifier zero knowledge, which means if the challenge is truly chosen random, then we can simulate. Okay, and then the anonymity, which is the same if there are 2 honest users, so the adversary or the service provider can only guess with 50%. Okay, then the advantage must be negligible. So, and then another part is we call security. It is kind of interesting in the sense that, so the same object, you define the properties from one perspective, just like what we have did. And then from other perspective, you would look like, it looks like, say from this perspective, you either look like an elephant. From the other perspective, it looks like a monk. Yeah, maybe there is no such thing like that, but it's kind of like that here. So from another perspective, we define security in the following sense. First is correctness, of course.